talking with Tony a little bit and discussing it with him, he thought he could assail you with core collapse talks, from now until the end of time. But my plan is to leave this afternoon, although I've enjoyed the time here with you guys immensely. And what he thought might be useful, and I agreed, was something in sort of the main track of this summer school about actually doing the work. So we've had the workshops in the afternoon, and that's certainly their main point, but we haven't had time to sort of talk about what doing computational astrophysics is going to look like for all of you in your future career. So Tony gave me this title and was kind enough to send it in, Mapping Multiphysics Problems to Today's Architectures. It's a perfectly good title. It's in fact a great title. I prefer this one, Killing Stars on Supercomputers for the Next 10 Years. And I'm going to try to convince you that although I'll talk a lot about supercomputers per se, the things I'm going to point out and that I hope you take to heart aren't specific to running simulations on the world's largest resources. They're in fact important for you to run a simulation, a numerical experiment on almost anything that you're going to be able to get your hands on over the next decade. So some strange things are afoot when it comes to computing. We've done some parallel programming so far this week, and for some of us, this was the first parallel running that we'd ever done. That's what I understood from the comments in the workshops, right? So we've been totally, I made this slide beforehand, we've totally confined our use of parallelism to domain decomposition, and we talked about that on Monday a little bit, and implemented with MPI, the message passing interface, a library that's in addition to any sort of serial language that you want to have. This is very much 20th century computing. This is what parallel programming was for the last 2.5 decades of the 20th century. It's not much different than learning how to program. This is actually the computer I learned how to program on. The first piece of silicon that I bent to my will was a TRS-80 Model 2 with Level 2 Basic. It was rara avis indeed in the environment I grew up in, which was way up in the mountains of southern Appalachia, but that's a different story. So nuclear astrophysics in general, we use a lot of supercomputing in this country and all over the world. So one way to talk about it is in terms of these so-called InSight allocations. So InSight is the allocation program at the two leadership computing facilities for DOE, at Argonne and at Oak Ridge. They're designed to be the largest supercomputing allocations on the planet, period. They're open to anybody on the planet. If I sort of count up how many CPU hours per year are dedicated to nuclear astrophysics projects, it's 152 million CPU hours a year, okay? That's about 10%, okay? So maybe that doesn't sound so impressive, but I mean just our field, and not very widely construed, mostly just stellar astrophysics, is 10% of all the cycles, when everything else is sort of contending for those cycles too. Climate, combustion, fission and fusion energy. Every other science field is sort of contending for those resources, and we get 10%. So why in the world is that? Well, we all know we have the coolest problem, but never mind that. Part of it's because we formulate large, important problems. We've been able to do that consistently. We've been able to build simulation models that are big and important, and we had demonstrated the ability to efficiently exploit these large computers. We're among the handful of communities that can actually make these things work, and you can actually get some return on your investment, if you will. That's why we get such a large chunk. But there's a question that I posit here at the bottom. Well, is this going to continue as computers get bigger and bigger and bigger? And a word that you'll hear a lot in my talk is the Xscale, right? So right now we have sort of petaflop speed computers. The Titan at Oak Ridge is 27 petaflops. There are lots of 1 and 2 petaflop computers now, lots meaning tens, low number of tens. Sort of the next big frontier that everybody's looking at, you go up 1 in a metric prefix sense, a factor of 1,000 from a petaflop to an exaflop. Same thing happens with the typical memories that are on these machines. They're approaching a petabyte. We have file systems that are tens of petabytes. So that's what I mean by the exascale. It's sort of the next big frontier, and we'll talk about that in just a second. And will this trend continue? Well, it depends. Can we continue to solve big problems efficiently? Okay? And this is a really important point, okay? And it's unfortunately you guys who get to deal with it. Because when I was a grad student, we had a situation that can effectively be seen in a paper that you can still find on the archive, and here's the number, okay? Because we were in the midst of Moore's Law, and Moore's Law still obtains. Everybody knows what Moore's Law is? Anybody not know what Moore's Law is? Good, okay? What you think is Moore's Law is not Moore's Law. Okay, it's like the Immaculate Conception. You think you know, unless you had theological training, it's not what you think it is. What you think is Moore's Law is Dennard scaling. That is, as voltage goes up, clock speed goes up. Moore's Law, all it says is that the number of transistors on a CPU increases, roughly doubles once every 18 months. Moore's Law still happens. Dennard scaling doesn't, and I'll explain that in just a minute. And it has consequences for everybody in the room. But back in the late 90s, these guys wrote this paper. They're all grad students at the Stewart Observatory at the University of Arizona. They're all my contemporaries. I know all of them. But what they noticed is that if you had a problem that had a fixed number of flops that you needed to do, you could either start running the problem today and wait for some amount of time at a given speed, or you could just slack off for about 18 months and then start running the problem, and your speed will have reached the point where you would get the same result at the same time, and you don't have to worry about coming to work every day for a few months, right? This really obtained when I was in grad school. Unfortunately, you guys are getting screwed out of it, and I'll explain why. You can't do this anymore. What's that? So this paper is great. I mean, they did a wonderful job. And like I said, all these guys are my contemporaries, and I tend to know them. So Chris Gottbrath now works for Total View Technologies. If you've ever used a big computer and used a debugger, he works for them. He was Arnett's grad student at Arizona. Jeremy Balin is now faculty at the University of Alabama. He just got there. He does simulations and observations of galaxies. Casey Meakin is at Los Alamos. He does stellar evolution. Todd Thompson, for his thesis work, did supernova modeling with Adam Burrows at Arizona, and now he's a faculty at Ohio State. And the only person I didn't know on this author list was this person, J.J. Charfman. And I was puzzled because I literally personally knew everybody else on this list. So I did what we all do nowadays, right? I Google stalked J.J. Charfman, right? J.J. Charfman has lots of publications. They all tend to be like this. It's hard to read this. So here's the title: Detection of Interstellar BS in the Cirrus Dark Cloud of the Numbum Association. And you can read the abstract. The first line's the money shot, right? Previous suspicions of large quantities of BS in large astronomical associations have been confirmed by observation. Okay, so maybe JJ just likes to do this, right? Maybe he just likes to write cranky papers. But you keep going down through his au revoir, and you get the same thing. On the utter irrelevance of LPL graduate students, an unbiased survey by Stewart Observatory graduate students, 2002. We present a new analysis of the irrelevance of lunar and planetary laboratory grad students at the University of Arizona. Based on extensive Monte Carlo simulations, we found that the actual number of useful results from LPL graduate students is $0 per, I don't know what units they're using here. Their irrelevance quotient far surpasses that of string theorists. So at this point, as entertained as I am by the idea of J.J. Charfman, I'm starting to get a bit suspicious. So I went ahead and asked some people, and my suspicions were confirmed, that in fact, J.J. Charfman is what you might call the snarky Nicolas Bourbaki of Arizona Stewart Observatory. Anybody heard of Nicolas Bourbaki? So Bourbaki was a pseudonym used by a group of young French mathematicians in the early 20th century who undertook a project to reformulate mathematics starting at first axioms. Right? So they were a group of people. They published under this single pseudonym, Nicolas Bourbaki, who apparently, I think there was some Napoleonic general that had a very similar name, and they liked it. But it was just the collective, right? And it was like other collectives, right? It was like collectives like Menudo, right? where young people, the group stays young, and they just move the old people out and just got new young recruits. So it's kind of like Logan. Anybody seen Logan's Run? Yes. Yeah, everybody. Okay. So everybody gets this illusion. Thank God. All right. But Bourbaki came up with a lot of cool stuff. I mean, the Bourbaki group were the first to introduce a symbol for the null set, right? They had a really cool notation in a lot of their publications. This, if you've driven in Europe any, you might see this on the side of a highway. It means a dangerous bend is ahead. And they would put this in the marginalia if there was a part of the proof that they were talking about that was especially difficult, right? So that's just an aside about J.J. Charfman, because I think that story is so cool. So back to what we were talking about. Graduate students of my ilk could just wait. We could wait for computers to get faster. Computers aren't getting faster anymore. They're not getting faster. Clock rates stopped increasing back in 2003, so we're going to dwell on this plot just a little bit. These Intel CPU trends, but the same is true for almost any company. So there's the clock speed is in dark blue here, and you can see, and this is as a function of time. You can see that curve's turned over and has gone flat. Okay, the power consumed has turned over and gone flat because it had to, and we'll explain that in a second. Okay, the performance per clock has even turned over and gone flat. All right. So the power consumed by a chip like this is proportional to the frequency that you run it at and the square of the voltage difference, the bias voltage between a 0 and a 1, basically. The voltage can't go any lower, right? Because we're already talking about bias voltages where things like tunneling really, really matter. So we're running all these CPUs at very low bias voltages and just giving them very small kicks to indicate a 1 instead of a 0. So we can't go any lower. So the frequency can't go higher. The power is capped by heat dissipation. These things get very, very hot, and power is money, real money. And we'll talk about that in just a second. So we all know that computers today, they run incrementally faster than they did in 2003, right? So where did that performance come from? Well, it came through increased parallelism on the chip, okay? So for example, does anybody know, do you know what the clock speed on your machine is?
2.27 gigahertz.
Do you know what the clock speed on your machine is? There you go. That's what. You know what the clock speed on that machine is?
It's over 2 gigahertz.
Yeah. Nobody knows, right? You knew. I'm sorry. You knew. In general, with a good tail of the distribution, nobody knows. The reason nobody knows is it's not that important of a consideration anymore, right? It doesn't tell you. It doesn't give you a good indication of what the relative performance of your machine versus somebody else's machine is going to be. 10 years ago, you needed to know the clock speed of the computer you were working on, right? And you needed to maybe step up. Today, it's not so important because there's a host of other considerations that are important. So just how bad is this power problem? Why are we making it so that nobody knows what the clock speed of their machine is? Well, I did a thought experiment. Okay, so this is Jaguar. This is the predecessor of Titan, the current second largest computer in the world at Oak Ridge. And when Jaguar was up, it had a peak speed of about 2 petaflops, all right? It sort of drew regularly, if you were running a job across it, 7 megawatts of power. It's pretty prodigious, all right? That's a lot more energy than the town I grew up in draws, and it's just a computer, right? So you can start doing some estimates. So a megawatt hour is about 3.6 times 10 to the 9 joules. Then if you go to the NIST website, you can see that a gram of TNT is 4184 joules, right? So a Jaguar hour is about 7 megawatts hours. That's about 10 to the 10 joules, and that's about 6 tons of TNT. Energy equivalent, right? Well, I want to do a supernova simulation. So I'd like to use Jaguar. For 0.6 Jaguar months, I get 2.6 kilotons. So I'm within 10% of the Trinity device. And the amount of energy I've expended to do a single supernova simulation. It's a preposterous amount of energy. Even when I live in the middle of TVA country where a lot of my power is generated by nuclear power plants and dams, this still gets expensive. really, really fast. And the heat that is dissipated is prodigious. But you know what? You should care about this even if you don't use this much electricity, okay? Because the guts of all your laptops are really not a lot different than the guts of Jaguar, or even the CPUs that are in Titan today. And the most immediate consequence of this is, with a modern laptop, if you put it on your lap, you got a good chance of getting burned. And it's really possible. So the amount of heat that's being dissipated by modern sockets is prodigious. And it just cannot continue. So this was recognized a while ago, that this trend just can't continue unabated. And so that's sort of what led to the design for Titan, right? And I'm giving you all the speeds and feeds. You'll notice that since we're in Tennessee, where athletics rule, we always have to relate the size of Titan to a basketball court. A football field would have been more appropriate, but you know, it looks kind of puny on a 100-yard field, right? It fills a basketball court, so it's very appropriate. So there's a whole set of speeds and feeds here for Titan. Of course, the most new thing about Titan is that most of its power comes from the GPUs. Most of its computational power comes from the GPUs. The CPUs are less than 10% of the total peak computational oomph of Titan. But there's something to note. So that, you know, there's how many petaflops you have locked up in the CPUs. There's how many petaflops you have locked up in the GPUs. But if you look at the peak performance, right, that's more than 10 times more peak than Jaguar had, Titan's immediate predecessor. But the amount of power that Titan uses is only about 2x total, right? I said 7 before, and I'd thrown in some other things in that. But you know, even at rest, Titan would draw 4.4. So I'm being generous and saying 2x. So we got 10x the peak flops for less than 2x the amount of power. That's why that is the only reason, really, that Titan has GPUs. This power argument. Okay? So even at this, the machine room at Oak Ridge, the power bill, you know, power is incredibly cheap in Tennessee. That's one of the reasons why these machines are in Tennessee, because we have so many hydroelectric dams left over from the TVA days and so many nuclear power plants. It's roughly a quarter to a fifth the cost of power here that San Diego supercomputing has to pay, and it's still, for Titan, the power bill every year is $2 million. Just the power bill, nothing else, not to pay anybody else anything. So, with all this in mind, the question is, well, what is the next set of big computers going to look like? Well, as the DOEs want to do, they had a series of workshops where people tried to peer into their crystal balls and try to figure that out. And so there's a handful of quotes here. So node architectures are expected to change dramatically in the next decade, becoming more hierarchical and heterogeneous. So that means you're going to have more things on a node than a regular old CPU, things like a GPU, things like a Xeon Phi, maybe something else. And they'll be hierarchical, especially in the memory subsystem. So there will be some cost to going to get an operand out of local memory, and then there'll be a higher cost for going to get an operand out of memory that's more remote. And you'll have to manage that. Somebody's going to have to manage that memory. Computer companies are dramatically increasing the on-chip parallelism to improve performance. Not the clock speeds, not the bias voltages, not anything else. The traditional doubling of clock speeds every 18 to 24 months, right, which mimicked Moore's law, which we talked about earlier, but doesn't obtain anymore, is being replaced by a doubling of cores every 18 to 24 months. And the systems will consist of 100,000 to 1 million nodes and perhaps as many as 1 billion individual cores. It's impossible for humans to manage that level of parallelism. I'll go ahead and just say that. Without considerable help, you just can't. So what does software they're going to run on machines today and into the near future, what does it have to look like? Well, you've got to exploit what I call hierarchical parallelism. Okay, so we already in the workshops we've already seen parallel programs that make use of MPI type parallelism between nodes, right? Domain decomposition. We've taken a set of colliding neutron stars, and we've divvied up the physical domain into individual pieces, farmed those out via MPI, allowed those processes to talk to one another, via the library and seeing how that's worked. You can also do it with things that are called PGAS languages, okay? Languages that are extensions of traditional languages like CoRE, Fortran. Titanium is an extension of Java. It's still the same notion. You're still going to rely on sending messages back and forth between nodes that are connected on a network. But modern nodes have other sources of parallelism, like SMP-like parallelism via threads. Anybody in here ever use OpenMP? There you go, so about half of us, okay? OpenMP is a way to exploit thread parallelism. That is, you have one heavyweight process on each processor that may communicate via MPI. But within that heavyweight processor, you have multiple threads of execution that can do independent threads of work. For a modern multi-core processor like everybody has on their laptop, it's a pretty good thing to map each one of those threads to one of those computing cores, right? And generally the hardware is congruent to that. That's the way you do it. But then there's another level, okay? And it doesn't matter if you're setting on a CPU, it doesn't matter if you're using a GPU, it doesn't matter if you're using an Intel Phi. It's what I'll call vector parallelism. That is, instead of doing operations on a single pair of operands at a time, you have to figure out some way to do operations on a vector of operands all at one time. And all modern processing thingamabobs have some way to do something like vector parallelism, okay? CPUs that like are in your laptops, they use special instruction sets like SSE or AVX, where they're able to take a vector of operands, so a list of numbers, another list of numbers, multiply them all together with a single operation and get some number in answers out, okay? GPUs change that a little bit. They're not true vector machines, but they're symmetric multiprocessors. So there's multiple threads that execute all at once on a GPU that sort of mimic that behavior. The Intel Phi is a special case indeed. So has everybody heard of the Intel Phi? Anybody heard of, if you haven't heard of Phi, have you heard of Mike? Right? Okay. So these Mike processors have many, many, many cores. So instead of 8 or 16, they have 60 or more cores on them. And they're designed to be programmed with OpenMP just massively, okay? But each one of the cores is fairly anemic. And it's pretty easy to figure out how anemic it is. An Intel Phi is literally about that big, okay? I know the scale of the fabrication of the transistors on that socket. It's 22 nanometers, okay? If I take that area on that chip and I divide it into 60 squares, I can count up how many transistors there are in each square, all right? Then I can compare that to historical processors, and what I end up with is each one of those Phi cores that's supposed to, help me do my work here in 2014 is about as fast as a Pentium 2, which is a late 90s processor. But the truth is they're faster than that because they can do these vector instructions. But if you don't do vector instructions on an Intel Phi, you end up with a pile of Pentium 2s, which is better than having an abacus, but only just. Okay, so you have to pay very close attention. So the exposure of unrealized parallelism in codes is essential to exploit all near future architectures. And it doesn't matter if it's a GPU, it doesn't matter if it's a Phi, it doesn't matter if it's a CPU machine. And uncovering unrealized parallelism and improving data locality, because moving data is expensive, it costs power, flops are essentially free in the modern world, improves the performance of even CPU-only code. So we took a handful of applications at Oak Ridge and ported them to Titan, right when the machine came up. And we started early, and it probably took us 1 to 2 person years to do those ports. It's less today, right, because we were in the middle of good compilers and good tools becoming available. But it's still months of work to do one of these ports. But most of the work is not in writing instructions to be executed on the GPU. It's in restructuring the code so you can see what's really parallel. And when you do that and you run it on a CPU, it'll speed up 2x. And I say 2x fairly confidently because all of these Vanguard codes that we tried out, every time we ran them on a CPU, they ran 2x faster than they did before the restructuring. just because you had to pay close attention to data locality. So, how should we program for these new systems? Well, we got to have good threading. So you have to do high-level threading. The threads must access close shared memory rather than distant shared memory. So that's part of that refactorization I just talked about, making sure that the data that you want to operate on at any point in the program execution is close at hand. And by close at hand, I mean not in another node's memory, not even in the most remote part of your node's memory, but hopefully in the cache, where you can really access it as quickly as possible. And you have to pay good attention to load balancing between those threads, because you don't want cores to go idle and just sit there generating heat. And you need good vectorization. Vectorization doesn't rely on having hardware that is described as vector. So that's, vectorization, you can think about doing vectorization for a GPU. And ultimately, when you write down the code, it'll be tens of lines, but that's okay. That's not a big deal. Okay, so everybody is nodding, and that's awesome. You should be a little depressed, right? Because this is not super duper easy. But I really am telling you have to do it. But there's good news. Okay, stellar astrophysics especially, explosion mechanism modeling for any number of things, stellar evolution, nucleosynthesis calculations, they're just absolutely rife with unrealized parallelism. There's tons of parallelism to be had in these problems because there's usually multiple degrees of freedom at every grid point that you've busted up via domain decomposition. All right? They're the exemplars of multiphysics application code. There's hardly anything more multiphysics than a supernova simulation. Typically, there's many degrees of freedom per spatial grid point, for example, and good examples from the problem that we've talked about so far this week, core collapse supernovae, radiation transport, and nuclear burning are really good examples of that. And the spatial domains typically are parallelized via domain decomposition. You cut the star up into chunks and distribute those among processes. Now, if you're doing other related computationally intensive topics like high density physics or nuclear structure and reactions or nucleosynthesis work per se, you're not quite as multi-physics, but there's still plenty of opportunities to realize unrealized parallelism, right? Especially nucleosynthesis calculations often rely on the ability to do linear algebra really fast. And we'll talk about that in a second. Linear algebra is a field that is rich in unrealized parallelism. There's plenty to do there. So don't worry, there's work to do. So not only is it good news for us generally, but it's also job security, right? There's work to do, right? And somebody has to do it. All right, so has anybody done any sort of hierarchical parallel programming? People have seen OpenMP, have you used it? Good. Has anybody used a GPU? So a handful of people. And the people who've used GPUs, have you typically done it with Cuda? Anybody done it with anything else? A couple people. So what would you use? OpenCL, okay. So let's talk a little bit. So right now, because we're still in the midst of this transition, there's a lot of different choices. A lot of people use Cuda to get their stuff on a GPU. Some people use other things. Something that we've pushed hard at Oak Ridge about is a notion of OpenACC, which is an analog to OpenMP. So it's a directives-based approach to doing GPU programming. It offers portability between a whole ton of compilers. It works for Fortran and C and C++, which is what you want. And it looks a lot like OpenMP, okay? It allows you to ignore, it's portable because if you're on a machine without GPUs, for example, you can ignore the directives, right? You'll still get crappy performance if you haven't restructured the code to make sure that you have good data locality, but it'll run just fine. And you don't have to change the source. You don't have to keep two things in your Git repository, right? And it's portable across different accelerators too, whether or not it's a GPU or something else. The whole point of OpenACC is for OpenACC to die eventually. The standards committee for OpenACC would like OpenACC to go away and for a lot of its construct to be subsumed into OpenMP. So there's only one set of directives that you ever have to use. Well, we're not there yet. So you can write a matrix multiply in OpenACC. I know you can't read this, but that's not the point. With just this many lines, and it's nice and parallel, okay? If you use Cuda, it's twice as long, okay? The coding is actually very, very similar. You just have to set up things and exit things a little bit differently. You're a little more responsible for doing explicit memory movement from the CPU memory to the GPU memory, but you're still okay. somebody said they used OpenCL. Here's the same matrix multiply in OpenCL. It's OpenCL, right? It's designed to be used across a host of different kinds of processors. Therefore, it's very extensible, it's very powerful, it's very general. What does that always mean? It always means you type more. But this is a problem, right? I mean, this is not an order of magnitude more lines of code, but it's 5 times more lines of code than the OpenACC. The more lines of code, I don't know about you guys, but the more lines of code I type, the odds of me making a mistake go up exponentially, right? And so this is actually an important consideration. So I didn't want this to be an advertisement for OpenACC, but just be aware that there's a lot of people who use Cuda, and if your problem is amenable to Cuda, those experts and things like online forums can make it a very profitable way to go. But if you're sort of in the wilderness doing something that not a lot of people have done before, think about using a directive-based approach, right? Because when OpenACC and OpenMP finally do merge, you're going to only have to change a handful of lines in your code, which will be a lot less painful down the road. Okay? All right, so we talked about the Xscale a little bit, but remember, even if we're not talking about the Xscale, the nodes are going to look like what you have on your desktop or down the hall in your department or whatever in the near future, because you don't have much of a choice. So these were the sort of the specs for posited Xscale. So this was supposed to be the exaflop machine that was going to show up in 2018. Guess what? Nothing. It's not going to show up in 2018. Okay? Things that are sort of 200 petaflopish are going to show up in 2018, and the Xscale is going to probably be, let's say, 2023. That's my prediction. I'll lay $10 on 2023. All right? You'll get people who will say 2021, and people who will say 2025, and people who will say never. But I'm going to say 2023. The problem is, of course, this line, like we've already talked about. We're actually allowing vendors now to have 200 petaflop computers that go up to 20 megawatts. And we'll probably give them another 10% to the Xscale and make it 22 megawatts, but they're not going to be able to do 30, right? Because at 30, you literally have to have a nuclear power plant to yourself. I mean, you really do. You would be building so many substations right beside your computing center that it wouldn't make any sense. And you really would need a small modular reactor at 25 megawatts or above, and that's what you're going to have. So 30's really a non-starter. All right, so it's got to be around this 20 number. The system size, it could either be 1 million nodes or 100,000 nodes. If it's 100,000, they're fatter. If it's 1 million, they're thinner. And the system memory, even at 32 to 64 petabytes, is going to be a lot fewer bytes per flop than you have on any machine today, even your brand new Apple. So that's going to be hard. There's a lot of things that we can do. So another one of these planning exercises, we sort of speculated on what we could do in the future going forward as we went from teraflop processing things to petabyte to petaflop processing things to things that are exaflop year sustained. We could go from doing multi-energy neutrino transport, maybe with coherent flavor mixing, and I don't think we're there yet. So we need to catch up. 150 species nuclear network, we're about to be there. So we're right around here. We're in good shape, but we want to do these things. And it's going to require significant work and algorithms and implementations. All right, so there's again, more job security up through here. But memory is going to be a big problem. So the easiest way I know to show this is to think about the scale of dynamic processes in a type 1A supernova, a thermonuclear supernova, where the interplay between the turbulence and the nuclear burning that actually powers that event needs to be resolved all the way down to the scale of the nuclear flame, which is like this, in a domain that's roughly the size of the Earth. So good luck with that, even on a sustained exaflop computer. So the total memory on the entire Xscale system is probably only be about 10 petabytes, and this is a figure due to Alexei Koklov where he says that it'd be good if you could figure out when a deflagration to detonation transition might happen in a type 1A supernova, but it's going to take at least 10 petabytes to do it, and you're just barely touching then. So you'd have to do a big simulation all over, and you're probably not going to go beyond this. So memory is going to be a big problem. And so that's okay, because all we need is models that have enough physical fidelity so that we trust every one of them. And what real science is doing lots of instantiations of numerical experiments and seeing statistical trends emerge from those data, right? So the ability to do many, many, many individual numerical experiments, as long as they have adequate physical fidelity, that's doing science. So you can make a claim that an exaflop system is going to be primarily most useful if you have good, strong scaling. That is, you can take a problem of a given size and run it in a shorter amount of time. And I suspect that that's what we'll mostly use a big exaflop system for. Okay, so there's one more problem. So we talked a little bit about in the workshops about how MPI sort of works, right? Each one of the individual processes does a chunk of work, then everybody communicates with one another. Maybe they're exchanging ghost cell information in a hydro simulation, for example, or any other kind of simulation that's explicit like that. And then everybody goes on their merry way and does the next time step till the end of that time step, and we all need to talk to one another. Okay, that's called bulk synchronous programming, right? So everybody is in lockstep with one another. One guy may get, one of the processes may get done before another one. If that's the case, he has to wait around while everybody finishes. So you have these synchronization points that occur. It's not really a viable path forward. Okay, it's already a huge problem, right? Flops are cheap and moving data is expensive. Flops are free, essentially, today, and moving data is the really thing that's expensive from a power, and that translates to real money. Even a perfect knowledge of the resource capabilities at every moment and a perfect load balancing will not rescue billion-thread implementations of PDE. So what I mean by that is that even if you knew exactly how long every single processor in your 10,000 processor job was going to run, and you could load balance it from the get-go, you're still going to pay too big of a cost moving that data around the machine, because the cost of rebalancing frequently is too large. It just costs too much in power and time to actually move data around the machine that much. So we need to take full advantage of an asynchronous algorithm where we assign individual pieces of the multiphysics to small tasks. So for example, in a core collapse supernova simulation, I probably can't move the matter via hydrodynamics at the same time that I want to do transport on it. But I could be moving the matter over some of the processors and be generating the Jacobian for the right-hand side for the left-hand side of the solve at the same time, because I don't need all the inputs and outputs. So I could do those at once and then have them wait at some point and then assign another task to be done later. So you need to create this notion of creating separate threads for logically separate tasks, things you can do in parallel, and filling this up. And then people who study this love to talk about directed acyclic graphs, which is a really cool word, but all it means is you have a list of nodes that are individual tasks that are essential to do a simulation, and you connect them with arrows that tell you which ones depend on which other ones. There are algorithms that let you traverse a directed acyclic graph and figure out what order you need to do everything in. So yeah, I took these quotes. So you could have a good example might be if I had a core collapse supernova simulator, right? Where I've got radiation transport that happens on a GPU between time step 1 and time step n+1, right? And I'm doing a Poisson solver for the gravity at the same time. There's stuff in a communication queue to determine what I need to do for the hydrodynamics, what pieces of data I need to pass back and forth during the hydrodynamics. And then I only sync every once in a while. But these things are all happening independently and in parallel. Whereas if I had something that was bulk synchronous, I would be doing many individual syncs all the way through there. All right? There's already examples that exist in other domains. Has anybody used Magma? So this is the GPU-enabled or PHY-enabled version of LAPACC. Everybody's used LAPACC, yes? Lots of people? Most people have used LAPACC, right? There's a GPU-enabled version of LAPACC already called Magma. It builds a directed acyclic graph to be able to do the linear system solve on each node. So it already sort of does this. Madness is a DFT code that's used for a lot of things. It also has a task list like this. Uinta is a terrestrial combustion code that was developed at the University of Utah that also does stuff like this. In operator split physics, the individual pieces of operator split physics can become these tasks. And you can just schedule big chunks of your operator split physics or sub-chunks of it. And so for multiphysics, it's not, at least logically, it's easy to figure out how to do it. Now, when you actually do it, yeah.
So can you think of it sort of like the Hadoop network where you have one node and you spread it out and then it comes back?
Yeah, it's exactly like so Hadoop is very much, so if you had a data mining operation that happened on a Hadoop cluster, it's you can break that down exactly like a DAG. Right, because there'll be certain tasks during the data mining that you'll need to wait and have a synchronization for, but others you won't. You can just send them out, have them execute as they will independently, and then every once in a while you're going to have a sync. So absolute, a Hadoop instantiation of a data mining operation is exactly a DAG.
There's Condor, which sort of has this.
And Condor does this too.
Sort of the dumb version of this.
That's right. That's right. But Condor was mostly used for when you had individual full-up processes. But it's a useful way to, it's turtles all the way down. So, absolutely, and it's sort of designed for individual programs. But it's absolutely the case, it's the same thing. Absolutely the same thing. Okay, so this is just a reiteration of what I just said. Will the Xscale be a strong scaling platform? I suspect so, because you won't have enough memory. The simulations will be larger. In the near future, we'll be able to do bigger simulations. Don't worry about that. I mean, I don't know if you guys want to do bigger simulations, but I do. But you're probably not going to have more than 10 times the number of MPI ranks than you have on the current biggest processors, right? You're just not. Because managing more than 10x the number of MPI processes we already manage is a little hard to think about. We're already, in Oak Ridge today, we manage 60,000 every single day, MPI processes and individual runs. So, maybe we do 500,000, but I'm sure as heck not going to do 6 million MPI processes. That's kind of crazy, because I can't think about how it works. And so that means, what does that mean, this sort of memory argument? That means that, for example, if you want to do hydrodynamics in 3D, you're not going to have enough memory to do resolutions that are much more than 2x in each dimension what you do today. So you're not going to be able to get fine structure that's an order of magnitude smaller than what you see today in a hydrodynamic simulation. But that's okay, because again, science is actually realized by exploring parameter spaces. So for our purposes, if we're modeling supernova, we can do large ensembles spanning things like progenitor mass, rotation, initial metallicity. We can do things like we can study different transport approximations and stuff like that. So just as a final note, when you actually end up doing a lot of this for a lot of different kinds of calculations, you end up with a ton of data. In some cases, literally a ton. So a DDN rack is about 2,000 pounds, I think. So you can literally end up with a ton of data. And so to manage these very large multiphysics simulations and the data they produce, you probably need a tool that makes that easier. So in the past, I've reviewed proposals for this Insight program that I told you about earlier, right? And we always make, and I know NSF does this too, that we always make people write down a data management plan. What are you going to do with all this data that you generate? How are you going to manage it? How are you going to try to get any sort of scientific insight out of it? And people wave their hands and say something that's mom and apple pie, and they leave it alone. But during the Insight process, we get to ask them questions about their proposal before we sort of assign it a final ranking. And so I often ask, what are you really going to do with all this data? And I've gotten responses back like, well, I have a great grad student. Who's going to, basically be running scopy and Globus FTP 24 hours a day without sleep. I have a great grad student. What you really need is some sort of software system that can help support that. And so we saw a need for that, and so we wrote our own, right? And we call it Bellerophon. So everybody knows that the name of our code is Chimera. So the name Bellerophon betrays a fundamental lack of classical education. in as much as Bellerophon killed the Chimera, and that is not our intent with this piece of software. But it's a nice portable Java GUI thing that lets us look at ongoing simulations all we want to. We can keep track of our subversion repository. One of the greatest features of Bellerophon in the way we've set up the SVN is that if somebody checks in code that breaks the code in our overnight regression tests, everybody on the team gets an email. Everybody's CC'd. The person who checked in that piece of code gets the blame mail, and he gets a trace back with hyperlinks back into our track that lets them see exactly where did you screw up. All right, so the big message I want you to take away, yeah. Not yet, but we're trying very hard. I will let you know as soon as it's possible because the future's now. Computers are not getting any faster. They're not going to get any faster. Let me repeat that. Computers are not getting any faster. Now, never's a long time. So I'm not going to say they'll never get any faster, but they're not getting any faster now. They're just getting wider. And it's true on the world's biggest supercomputers, and it's true on your laptop. This choice between whether or not you're going to put your code on a Xeon Phi machine or put it on a GPU or put it on a Blue Gene, all this panoply of different platforms you have available to you if you've got an allocation at various supercomputing sites over the world, yeah, the specific implementation matters a little, but we're talking about tens of lines of code. The real work is no choice at all. You're going to have to do the same thing. You're going to have to do an uncovering of the hierarchical parallelism that's available, period. And the rest is details. And it really is details. I mean, it's literally tens of lines of code, even for a code that's 100,000 lines long. In a lot of cases, you can change tens of lines of code, as long as you've done all the restructuring, right? Bulk synchronous execution's horrible. Let's try to get away from it. And managing large simulations is something we can barely do now. So I don't know about how we're going to do thousands of them, tens of thousands or hundreds of thousands, which is likely what we're going to do at the Xscale. And we shouldn't rely on people to throw solutions over the fence, and that's sort of why we've taken it upon ourselves to roll our own, but we'd like to share. So with that, thanks very much.
You mentioned it before, an exaflop machine is not going to have an exabyte of memory, it's going to have tens of petabytes of memory, 64 petabytes. So, you mentioned the 1.8 problem, at sufficient resolution, you'd be of order 10 petabytes. In the supernova problem, our supernova problem, the Jacobian can be 30 petabytes if it uses that approach. So the machine's going to force us to spread our problem over of order half the machine.
At least, for memory.
Yeah. And so with regard to the task-based and DAG-based approach, certainly you see how that basically gets you away from both synchronous approaches. But with regard to data locality and data movement, as we're getting forced over half the machine, even if we have different processors functioning on different tasks, there's going to be a lot of data movement that has to be, because we're being forced to,
right,
to
but
be non-local.
so then it may well have to be that the data that we pass back and forth is executable code, so that the data stays where it sits, and executable code actually gets shipped across the network, which is going to be a smaller amount of data. But yeah, as long as you the stiller you can keep data, the better off you are.
So you're moving
The execution to the data.
and not the data.
Yeah. Which is in some ways what Hadoop already does for trivially parallel things, right? It goes out and you send a little executable out to go and do something on an HFS file system, and it's done. Mike.
So you made the comment that in the future we had to move away from bulk synchronous parallel execution, and I agree with that. But do you see MPI going there?
So there are noises in the standards body that they understand this. Things like non-blocking collectives have already been added to the standard. So it's not completely clear to me that you'll be able to implement this effectively using MPI, but I'm very confident that we're going to have to try an MPI first, because if we don't give it the first try in MPI and just wait for something to come along, we won't be ready. So I suspect it's harder than MPI than it is in a variety of other ways that you could figure out, but you're going to have to give it a try using MPI.
Do you see anything else coming down the pike? I know Tom Sterling is working on a new paradigm.
I think that those ideas are pretty useful, and I think, you know, among those DARPA HPCS languages, I think the one that might have the best chance of surviving in some form, it won't have the same name as Chapel, things like Chapel could be something that you could implement a task-based approach in.
I have a couple of questions. Do you try Xeon Phi, and how do you compare Xeon Phi with GPU? And another question is, how often do you move data from GPU back to your main memory?
Right. So the second question is as little as possible. Right. You want to try to keep everything out back there.
You mentioned that synchronization point, and at that point you only pass very little information back. Would you?
Yes, usually you try any approach. So like one of the things we're doing is try to get the whole Jacobian out there for nuclear burning, trying to get the whole and only pass back the solution vector every once in a while, and that's it. So we actually want to try to build the Jacobian out on the GPU, do the solve out on the GPU, and never send anything out past the first malloc of that memory, and only send little pieces back. Now in the future, the bottleneck between a CPU and an accelerator, it's going to get less. The bottleneck's going to go down. We're going to have wider paths, right? You're still going to have to worry about memory locality. It's going to be like using a NUMA machine, but it's not going to have to dominate your thought about how you design your code. So I'm pretty sanguine about that. I think that's going to happen, but you still have to worry about it. And then your previous question was. Oh yeah. So we've done just a little bit of Xeon Phi programming with the Supernova codes. I have access to some results from other people, and it's consistent with what's seen in the literature. For most codes that are already extant and have done, say, a GPU port or have done a Xeon Phi port, and then they've done the other one, right now, people consistently find that the GPUs in general give you about 2 times the performance of a Xeon Phi. And I don't think that this is a huge mystery. To really engage those Xeon Phis, just like I said before, you have to make sure that you get the vector instructions running. So if the code you're running on the Phi is at all scalar, it's going to go slow. It's going to go at the speed of a Pentium 2. Whereas on the GPU, you actually have to do the management of the threads yourself, and you sort of know exactly what they're doing. On the Phi, you have to rely on the compiler to generate the instructions for you. And the compiler will give up if it isn't 110% sure that it can vectorize an operation. So I think fairly consistently people have seen differences in almost exactly 2x between the latest generation of Intel Phi and the latest generation of GPU.
One of my students actually benchmarked Xeon Phi and GPU. What they found out was for simple addition multiplying, the peak performance is comparable to GPU.
But I believe, yep.
For sine cosine, it's probably like a third, and for logarithmic, it's probably like a tenth.
Yeah, because there's impossible to vectorize.
When you say 2x, is that core to core or board to board?
It's node to node.
Node to node.
Node to node. You know, controlling for similar CPUs and things like that. Yeah.
This isn't to say that the mics can't, even today, can't be as fast as the GPU. You're just saying that to the person who's, you know, trying to implement one or the other.
Yeah. Yeah.
This is really the best you can hope for without, you know, being an expert.
Exactly. I think what people have learned is to get the code running on a Phi is bone simple. Much simpler than it is to get it running on a GPU. To get any performance out, it's actually much harder because you have to lead the compiler by the nose. And therefore, you do have to have a little bit of expert knowledge. For example, you have to make sure that things are aligned in memory correctly to be able to effectively get the vector operations. So to get that zero sort of thing, just make it run, really easy because the compiler just does it. To get any performance, really hard, especially compared to the GPU.
I'm just wondering, because of DAG and upcoming like Amazon S3 and all these things, will that actually help at all, or are those too slow? I mean,
So, I'm sorry, what,
You can buy from Amazon vast amounts of CPU time,
right.
and same from Google. And the question is, is that just too slow? The next days are just too slow.
It's problem dependent to some extent, but it's true that a task-based approach would hide the latency and even the bandwidth of the network you're talking about. So maybe the network isn't as important going forward as it has been in the past.
I think it's a no process. You can parallelize everything. Our problems are.
Yeah, trivially parallel, yeah. Yeah, which is great. I mean, so you probably don't need to pay up for a high bandwidth, low latency network on a big supercomputer. Why not use Amazon for that problem? Yeah. Anything else? Okay, thanks very much.